Welcome everyone to this instance of the CI Compass webinar series. I see a lot of familiar names and a lot of new ones. Welcome. So today we have speaking Chris Bontempi, who's the Director of IT at the Network for Advanced NMR, Nuclear Magnetic Resonance. One of those really cool places where physics and chemistry collide. He's at the University of Connecticut Health Center in Farmington. Chris has worked primarily in large-scale commercial software development, focusing on healthcare informatics and data engineering for the largest provider of healthcare software in the U.S. In his over 20 years as a principal software architect, he's led a team that developed analytical systems across the entire healthcare sector, working with thousands of customers to determine their needs, challenges, and aspirations. More recently, Chris was part of a team working in the energy sector, exploring ways to modernize and expand their markets in anticipation of the wholesale worldwide changes taking place there. Currently, Chris is part of a team whose mandate is to collect, organize, and share data produced by NMR spectroscopy, and that is big data writ large. Initially at UConn Health Center, University of Georgia, and University of Wisconsin-Madison. General goal there is democratizing the effective use of NMR spectrometers. Through these experiences, throughout them, the central emerging theme has been how to make observations, the data that we collect from them, useful. His experience with system architecture, system operations, administration, data engineering, large-scale complex software development and support, all the myriad IT principles and best practices underlie these pursuits. Some like security, availability, ease of use, accuracy, reproducibility, reliability, supportability, all these abilities that we strive for. They've all given him a productive perspective from which to work on these challenges. He has a combined BS degree in computer science, sociology, and political science. He is exactly my kind of multidisciplinary person, and he is celebrating his 40th year as an IT professional. So he's been around even longer than I have. Chris, I'm really looking forward to this. I've heard little bits of what you're going to talk about, and I'm excited.
Well, thank you, Eric. I appreciate that. I'm going to jump in and get started. Thanks for the introduction. I want to acknowledge that NAN, the Network for Advanced NMR, is an NSF mid-scale project, and that's my current home. A lot of what I'm going to talk about is past experience. So let me get started with that. The objective for this particular talk is to basically explain or answer the question, what considerations should I have when building a large-scale database? So I've generated an answer for myself to that question, and I think I'm interested in what everybody else's answer to this question is. That's part of my objective. So I'm going to share what I think, and hopefully at some point we'll be able to exchange ideas of what you think the main considerations should be. Here's a basic outline of what I'm going to say. I'm not going to go through this in detail, but this is essentially what you'll be hearing about in an outline form. So I'm going to be talking about lessons learned, and that's primarily in the past. So the question is, what am I going to be sharing about? And really it's collecting, organizing, and providing data from a variety of sources to a variety of consumers for a variety of different purposes. I think this is pretty common. It's pretty rare that you share one kind of data to one sort of audience for one purpose. There may be other kinds of combinations involved there, but truthfully, it's pretty rare that scopes are narrowed to that extent. The context of the lessons, as Eric explained, I work primarily in medical informatics, and I'm going to be talking about my experiences with a platform that we built. It had multiple views, if you will, clinical, financial, operational. It dealt with large-scale hospital systems, clinics, pharmacies, offices, so a variety of audiences. The time span for the project itself was about 18 years. And in that time, we had access to an availability of about 20 to 35,000 technologists. The company itself had an 80 to about $120 billion annual revenue. And the R&D budget for software was somewhere between 300 and 500 million typically. Would vary from year to year depending on what was going on. So this informatics platform, where I'm drawing most of the experience from, started out 100% relational. Was if you go back, around the turn of the century, it was a 100% relational enterprise data warehouse was conceptually what we were trying to build. It was built initially on Sybase. I ported it to SQL Server, which was a relatively easy port because Sybase and SQL Server share a common origin. And then we ported the whole thing to Oracle, and it sold very well. It was a popular product, but it hit a huge number of limitations. And so it forced us to start looking in other directions. And at that time, maybe 5 to 8 years later, we started looking at what would typically be called NoSQL type solutions. We settled on Cassandra. And then we had an upheaval in the R&D group and purchased an organization out of the Silicon Valley that was building a homegrown graph database out of C# and the .NET suite of products. That project went on for a few years and essentially became untenable. And so we were looking around for a much greater foundation. And we found it in essentially what we call big data platforms these days. And it essentially turned into an industry-leading product based on this. So in that time, or since that time, I've built 2 other similar systems based on these principles. So what I'm talking about here is not just theoretical in terms of, hey, I think this is a good idea. It's more, we thought this was a good idea. We went through a lot of it. We were successful with a lot of it. We definitely found problems and limitations. And out of this is kind of where I'm getting the idea that I think there are some things that it's helpful to focus on. I want to touch on the solution itself, just to say that the origin of it was this big table white paper in 2006 with Fei Chang and the other folks at Google. And Google typically, I don't know how different it is now, but certainly in those days, they weren't open source. They don't share their technology directly, or didn't share their technology directly with anyone. So this was just a white paper that had almost no implementation details. But it was interesting enough and pivotal enough that it just blossomed into a gigantic treasure chest of technology that we were able to leverage. And I'm going to get into more of the details of that towards the end. But I just want to kind of frame it in saying that this is essentially the foundation of that solution. So I'm going to switch gears a little bit and talk about a conceptual framework. This conceptual framework came out of creating these solutions. So this is more a way of explaining how I think of it, and it might be helpful in understanding the rest of the discussion. So basically, we start with acquisition and consumption. This is, your typical, input output model. Things come in, things go out. Pretty simple. As far as the acquisition side, I'm going to frame this in terms of the projects that we're working on now. But these projects aren't built on this solution or this set of solutions. But I'm just going to use it as a kind of a topic situation so that you can kind of ground what I'm saying to some extent. So in the current situation, in terms of acquisition, we'd have things like spectrometers or devices that are sending information. We've done this with IoT devices. You can do it with basically anything. You also have a class of information like facility information, where people would, type in information at a website or enter information in some way. That's still an acquisition process. And then we also have, in this set of things, we have a knowledge base and knowledge base information, which for the purposes of this discussion, we can kind of consider to be somewhat like Wikipedia, where there's a treasure chest of knowledge that we're sharing. People can contribute to that. They can, submit corrections, perhaps, things of that nature. All of these are acquisition type activities. And from a conceptual standpoint, we're going to talk about the acquisition action and the data at acquisition. So that's what this box is meant to represent. This is the information that we have in its state at acquisition. On the other end, we have consumption, where we have typically users. You might have systems consuming an API, however you're going to be sharing information, however the data is going to go out or the information is going to go out. We have those consumers at the consumption end of the pipeline here. And the data at that end is, I'm going to refer to as data at consumption. So we have data at acquisition, we have data at consumption. So I'm going to talk about principles in this framework, and principle number 2, which we'll get to principle number 1 at the end. But principle number 2 is that for the most part, data at acquisition is not the same as data at consumption. This is true of most systems of this type. If it was, you could just use Dropbox. I put stuff in there, you take stuff out. It's exactly what I put in there. That's fine. Most systems don't function that way. Most systems require something in the middle. And for the purposes of this discussion right now, I'm going to just call this whatever. So we have data at acquisition, we have data at consumption, and in between them, we have whatever. And that's generally the flow of the data through the system. Now, the reason I want to conceptualize it this way is that this principle number 3 is the separation of concerns. So the concern of things at the acquisition end is that data gets acquired properly, that you get what the spectrometer sent, that you get everything that the spectrometer sent. Nothing got dropped, nothing got altered. We have to think about things like scale in terms of data coming in. We have to think about storage. As things are coming in, we got to make sure we have enough storage for them. I mean, there are a ton of considerations at the acquisition end of things. These considerations don't affect directly consumption. There are a whole set of other considerations at the consumption end. What does this user expect to see? What does this user expect to see? Are those two things the same? Are they different? How are they different? And then this whatever piece in between them is sort of the glue that sticks them together. But this principle is very important because the act of acquiring information coming into the system is by itself, in most cases, monumental. It takes a lot of time and a lot of effort, and it doesn't need to be freighted with the considerations on the consumption end. The fourth principle here that would make this system the most functional is that the data acquisition is immutable. Essentially, whatever your acquisition systems are providing is exactly what data acquisition is. You don't modify them. And thinking back to principle 3, if this user wants to see, I'm going to use a really simple example. If they want to see all of their temperature readings in degrees Fahrenheit, for example, and the spectrometers provide them in some other unit like Celsius, the separation of concerns would say, you don't modify this value coming in from Fahrenheit to Celsius. You store it exactly as it comes in, and it's immutable as that value. This piece in the middle is what's responsible for turning it to what the consumer wants to see. And I'll talk about how to uncomplicate that idea, because I'm sure it sounds complicated right off the bat. So these two things work together, your separation concerns and the data that's immutable at acquisition. Principle 5 is that this box I'm representing as whatever needs to be 100% safely repeatable from acquisition to consumption. That means you can run this as many times as you want over the exact same data, and you'll produce what you need to produce and not damage anything, not overwrite anything that wasn't supposed to be overwritten. Part of the feature of whatever is that it can change and evolve over time. So it may change the data at consumption if that's appropriate, if, for example, it was incorrect in the first place. But it's very important that this be safely repeatable at all times. Principle number 6, no schema penalties anywhere. If we're adding information to the system, you can't have this piece in the middle break. You can't have the pieces at consumption break. No schema penalties. Schema is going to evolve and change. So plan for that. And then this is where we end up with principle number 1, which is the direction of design. So it's important that you understand the use cases of the consumers and that those considerations push back through the system and that each level of the system supports the previous layer. So the data at consumption has to support the act of consumption. This whatever piece has to support and provide the data at consumption. The data at acquisition has to support this piece in creating these. And the acquisition itself has to support getting that data. So that's the direction of the data flow, but the direction of the design is backwards. Start with what you want here and look at the other pieces and make sure that they can provide what's necessary. And again, that doesn't mean that you create the idea of the consumption here. The consumption always stays here, but it informs the acquisition. In other words, you're not going to be able to consume something that you can't provide. So make sure you understand and know that. So that's a conceptual framework of this, and I'm going to talk about how we can make this happen. But I do want to touch on this analogy, and basically the analogy of the system, it's not quite in as widespread use as it used to be, but the idea of a data lake is kind of what this is. It's more of a data engineering platform these days. But one aspect of this analogy I wanted to call out, which is this idea that water is water. And that equates by analogy to the idea that data is data. And when you're building a platform and thinking about a platform, it's useful to think about the essential properties of data in the way that if you're working with water, you would work with the essential properties of the water, not with how it's going to be consumed. So for example, in the analogy, water is consumed at a sink, at a bathtub, in a water cooler, in a water fountain, the Trevi fountain, cases of bottles of water. These are all different manifestations of consumption of water. But if you're moving water around from one place to another, you understand it has weight. There's things like pressure that have to go into the piping systems. There's filtration. There's relief valves. There's all kinds of things that deal with only the aspect of water that's water, essentially, and doesn't need to deal with any of this. It's only when you get down to the consumption part of it that you start to deal with some of these details. So that's the part of the analogy that I find useful. Some of these other things that folks have talked about, like, you know, swamps and puddles, and it got a little silly at times. But this piece, I think, is quite important. So to that point, what are the essential properties of data? The good news, I think, or perhaps not so good news, is that there's no universal list. I think there's a lot of things that we all agree on, but the important aspect of this to me is that that we get to decide what the essential aspects are, what's essential to our enterprise, to what we're building. Some examples that I could give you to kind of flesh out the idea of essential properties of data are things like scale, precision, and limits. If somebody is reporting a human body temperature of 50,000 degrees Fahrenheit, we know that's not reasonable. So that's a limit that we can make an assumption about. Things like localization, aggregation methods, provenance and lineage, so that when people look at your data, they find it credible and reliable. Persistence and longevity. How long is this data useful? How long do we need to keep it around? More prosaic things like security, operational ideas like readiness to hand. These are all ideas of essential properties of data. And a platform like this needs a focus on those things because they're going to be essential to providing the capabilities that people will need. Focusing on that in terms of the platform rather than on one specific application need, which is, I think, going to limit the usefulness of what you're building. And it has, in fact, done that many times. So how do we accomplish some of these things? It's through this idea of a data promotion model. So you'll see in this graphic here that at the bottom, we have this level 0, which is that data at acquisition, the immutable archived as is data. And that's our first level. That level is almost not really useful to anybody directly. At the other end, we have the data at consumption. And I've added these boxes that are essentially domain drivers or domains of data. So if you think about your data at consumption being broken down into somewhat smaller, but not tiny and minuscule groupings. So things like a knowledge base grouping or a knowledge base domain, an experiment domain, a facility domain. And then how do we get there? Well, we get there by going through multiple levels. And these levels that I've defined here are not sort of fixed. They're whatever you need them to be. And I've proposed as an example that perhaps our first level would be filtering, cleaning up, naturalizing the data to a state that we know is going to be useful to people. A second level might be staging for searches. So we take the data and organize some of it, index some of it, so that it's useful for searches when people are looking for particular kinds of data. And then this level 3 is the idea of domain prep. Again, these are just examples of moving through these levels. The thing that moves them through these levels is that whatever piece, this safely repeatable piece that can take things through different levels, take your data through different levels. So for example, if you had a data item here that essentially manifests or appears, materializes at level 2. So it didn't exist at level 0 or level 1 yet. It materializes at level 2 based on information that it gets from level 1. And that piece of information then goes into this and all these different pieces, because it's at level 2, it's going to be present in all of these places. So if you change this particular piece of data, it will need to change in these other places. And that's what this functions to provide, this whatever piece. If you had a piece that was only at this level 3, then it would only need to change at these 2 levels. This is a way of economizing this denormalization of data, if you will. And you'll want to be able to track that, but it leads us to another principle, which is that denormalizing isn't a crime. In fact, it's a good thing. It really helps to facilitate this breakdown of information across multiple domains to make it sensible to use. But it's also not really an inherent value or an inherent virtue. So it's something to use judiciously. It's not free, but because it's not free, that doesn't mean you shouldn't use it at all. It's something that we want to use appropriately. So talking about the domains and what I mean by domain drivers, I've got some examples. And again, these are pulled from my current project set. And essentially, these are viewpoints from various different roles or personas who might use the system. So I've created 4 of them just as an example. I have an experimenter, I have a facility manager, I have a PI, and I have a knowledge-based user / contributor. So the things that my experimenter is interested in are their own experiments, all the experiments that were performed on a particular sample, perhaps, all the experiments of a particular type using a particular pulse sequence, all the experiments that were done on a particular instrument. This is the perspective that I would expect our experimenter to have on their data. A facility manager has a different perspective. They want to understand usage statistics of their instruments, to understand things like appropriate or better use. I see this person is doing this kind of experiment on this particular spectrometer, and it's not really appropriate. They're not going to get the results they want. So I want to tell them about that and help them with what they're doing. Things like grant reporting. What's the usage of what I have? Support for the next grant. What could I put in here? Can I get another instrument that would be able to cover some of the demand that I have? that would make it very useful. And then things like maintenance problems or prediction. Do I have a probe that's going out? Do I have an air conditioner that's starting to work inefficiently? Things of that nature. So that's a facility manager perspective. PI's perspective, what am I spending on NMR usage? What sort of results am I getting under the different grants that I manage? What skills do I need to hire? What kind of spectroscopy do I expect I'm going to need in the next year, because there are some innovations happening and I want to be able to engage in that. And then, of course, support for the next grant. So that's a PI's perspective. And then a knowledge-based user, understanding NMR, experiments or protocols that I want to do, protocols that I might want to share as a contributor, and I want to compare my protocols to other people's protocols. How is what I'm doing different? So you can see these are all pretty rich roles with interesting perspectives. And the goal is to be able to provide these perspectives or data that satisfies these perspectives from the same source. And that's why we want that data promotion model. That's why we want these different domains that people can tap into. If you start with one perspective and build your system based on that entire perspective, it's going to be very hard for you to address these other perspectives. And that's been a common approach. Hey, let's just start with something simple, and then we'll expand on it as we go in. And what really happens is it limits the system, because you've built this perspective into the entire system, start to finish. So that's something we want to try to avoid. I want to mention some orthogonal concerns, because you really have to focus on these things. And it's important to understand the perspective that you're coming from. So from my perspective, the solution needs to be as simple as possible, which usually means the fewest moving parts. But it has to be simple without sacrificing use case fulfillment. It's very easy to build a simple system. It's not easy to build the simplest system that satisfies the requirements. And that's what's really important here. So don't lose track of this second half of that sentence. You need an emphasis on good DevOps principles, and this talks about that repeatable whatever piece. Ideally, you got to be able to go from total annihilation of your system to fully functional again in hours, not days. So think about that as you're building your system. Don't think, well, this is just an additive system and it only takes, a couple of seconds to add new data. Think about what it's going to take to rebuild the whole thing from scratch. And of course, you have to build in operational reliability. If someone comes to use your system, it has to be functional. You can't tell them, hey, you're going to have to wait a couple of days till I get it working again. Best security principles, obviously this is important in terms of reliability. If you don't have good security, people aren't going to be able to rely on what you're providing for them. And then golden mean agility is, again, another very important piece of this. So there has to be very low friction for new data sources. If I add a new instance of a spectrometer, it can't take very long to do that. If I add a new kind of spectrometer that's different from the other spectrometers, it can't take very long to do that. Lowest friction possible for new use cases. So this is at the other end. So I was talking about new data sources, so that's at the acquisition end. At the consumption end, now I have a new role, a new person who's finding, that they might find this system very useful if I can provide this set of information to them. So again, lowest friction possible to be able to do that. In terms of practical considerations that inform those, the other considerations that I've talked about, including the orthogonal ones. Ideally, or in this situation, practically speaking, you need to have an automatic ingest discovery mechanism. So as data comes in, your system has to recognize that it's something new. And of course, the system's not going to be perfect at that all the time. So you're going to need a manual curation option. Automatic metadata discovery. So yeah, you've got new data, and now you need metadata about that data. You should be able to detect most of that yourselves, or your system should be able to detect it automatically, again, with the manual curation option. Self-service discovery and consumption of data. So for a user or a consumer of data, they have to be able to see these things that are coming in and be able to make sensible use of them without a lot of extra, IT type effort. System has to grow on its own. And we ourselves have to make a distinction between anonymous and authenticated users, because anonymous users are going to be able to see a small part of the system. Authenticated users theoretically could see more of it. Some of them can see all of it. So you have to make sure you make that distinction with this discovery process. Data quality reporting in terms of practical consideration. What am I getting? What's reliable? What's not? That example that I gave about body temperatures being 50,000 degrees Fahrenheit. If you have a whole set of data that represents diagnostics for people, and you have their temperature readings in there, you should be able to tell a consumer of this data, hey, about 500,000 of these records have body temperatures that we find suspicious because they're out of a normal human living range. You should know that going in. They should be able to discover this going in, rather than bringing the data down, doing whatever analyses they're doing, and finding those kinds of things themselves. The consumers of your data should be able to focus on the question that they have, not how do I determine how clean this data is before I even get started. That's a big piece of this, and it's doable. It can be done in an automated fashion. We've done it with machine learning in the past, and it's very effective, much more effective than we ever expected it would be. And then packaging options, you have to deal with the fact that people are going to sometimes come and look for a couple of small things, maybe one thing, maybe two things. And then also deal with the fact that they may be looking for a tremendous amount of things, the entire database, if that's possible. So consider your packaging options, think about that going in. And I mention this because it's easy to design a system with a particular packaging approach in mind, and then miss the mark drastically. Because you've only worked on small distributions and haven't really thought about large distributions, and then your system can't support the latter. It becomes difficult, and it goes both ways. So those were some practical considerations. I just want to throw out some ideal features to work in the direction of, or that I think a lot of people work in the direction of, and that you want to keep in mind. These are things that go across all the different domains. So smart discovery or context-aware discovery. Who's looking at the data? What are they going to expect to see? Going back to that temperature example, we have one type of user who only ever expects to see temperatures in Kelvin. So let's make sure that when we're showing it to them, that's the default. Have that ability to distinguish between different roles and different people who are looking at the data. There needs to be low latency from discovery to use. So by discovery, I mean I found all the data that I was looking for. Now I want to start using it. You want to focus on very low latency there. You don't want that to be hours or days between discovering what I want and actually making use of it relatively quickly. And then little or no penalties for do-overs. Hey, I got a bunch of data. It's the wrong stuff. I need some other stuff too. It shouldn't take me very long to go back and get what I'm looking for. A self-service feedback loop. So for the representation of data, a user may suggest an alternative representation. You've got this data listed as this thing. I think it's more useful if you list it as this other thing. Make that self-service. Allow them to be able to do that. Not overwriting the data that's there, but creating an alternative view of that data that shows it in this representation that they think is useful. And then same thing for processing, not just the representation of data, but how this data was derived. So we may have data items that are derived there, and you might say, I'm looking at this and you use this algorithm. It's a little bit out of date. Maybe you should update it and use this new algorithm. Again, ideally, this would be self-service, so that a user could create that, suggest it as, if you're familiar with the GitHub idea, suggest it as a pull request of some kind and say, listen, I think we should do things this way. And if it's generally agreeable among the people who use it, then you could pull it in and make it useful very quickly. And then from a heuristic standpoint, being able to look at the system and how the system is being used and help people in their use of the system. Hey, you know, I've noticed you're using this thing over here. This is similar and it might help you. Or a lot of other people are using this other thing too. You know, sort of like an idea of top search results. This is a way of helping the system help the users based on what they're doing and what other people are doing. And again, an ideal feature, I know it's something that we're all kind of familiar with, but you want to be thinking about this when you're talking about large amounts of data, because everything is costly with large amounts of data. You want people to be able to get to answering their own questions as quickly as possible. So circling back to this idea of what this whatever box was, I really do mean that it can be anything. Essentially, it's a data engineering platform. It treats data as data and the essential properties of data. But I want to talk about what it's been most recently, and perhaps there are new approaches that would make this even better. But important aspects of this piece are that it's pretty scalable because you're going to continuously collect data, and therefore it probably needs to be parallelizable. It's scaling vertically is probably not going to satisfy all of the requirements of the system. And from my perspective, it needs to include results consolidation. I know there are lots of things that parallelize, but they kind of leave each piece where it is. I think there needs to be consolidation. So to that point, I want to talk about what this whatever has been in my experience in the last few projects that I've done. You know, again, it was a technical evolution that started with this big table white paper. And I'm explaining this way because there's no way to really have one name for this that describes what all of this is. A lot of it's dependent on what you're doing. So it started with this big table white paper. This spawned a ton of Apache open source projects, Hadoop being kind of the centralized one. But you had things like Hive Server and Pig and HBase and Squoop and Flume and Uzi and all these things. Mahout, Cassandra, you know, a bunch of other, you know, traditionally NoSQL database type situations in a lot of different ways, document databases and key value pair databases and graph databases, many different ways of looking at data. And a lot of these were based on a common set of ecosystems. So this MapReduce idea, Zookeeper as a way of organizing disparate pieces, things like Yarn as a processing environment, HDFS as a file system, Hive Catalog as a relational database type system. And one big part of this was this idea of a serializer deserializer, which essentially allows you to consume just about any format of data you can think of. And I've listed some of them here. Some of them obviously text-based, you know, higher latency. Some of them are also binary based and much lower latency, things like ORC files and Parquet and things like that. But also other forms of data coming in, things like Kafka streams. So it's possible to build a relational database on top of a Kafka stream, for example. It's actually fairly common, which is a pretty interesting approach to problem solving if that's your kind of problem domain. But anyway, so as these things grew, you had a group of major contributors, companies like Facebook and Twitter. You didn't really see Google doing this because they didn't, like I said, at that point, they weren't really participating in any open source projects, or if they did, it was pretty minor. But Facebook and Twitter, LinkedIn, Uber, a lot of those companies that were dealing with tremendous amounts of data really put this stuff through a trial by fire. So a lot of it's very mature in how it does things. It was a very active crucible, as I say. And then a company came along, or a group came along out of Berkeley called Databricks. They spun off of Berkeley, Cal Berkeley, and created this company, Databricks, and created Spark and Spark SQL, which replaced a lot of things here, but also leveraged a lot of this infrastructure. And it also opened up work from a language standpoint, because it was mostly Java before that. And this opened it up to PySpark, Python, and Scala. So that actually helped to expand the use of a lot of these systems and actually make them a little bit simpler. So the Java implementation was a little complex. The next step in the evolution was companies or groups collecting a lot of these pieces together into distributions. So you had Cloudera and Hortonworks and MapR. They would include lots of different pieces from here, and their special sauce was basically showing you how to make it work and work effectively. And this is also something that Databricks would do for you. But they added some of their own pieces. So things like Impala and Jupyter Networks were added to this ecosystem that didn't come from any of these other places, but they became, and some of them weren't open source, like Impala is not open source as far as I know. It might be now. But it's a very good and reliable relational database type server based on this technology. So for example, you could put Impala on top of a Kafka stream based on this infrastructure. The next step in the evolution was to cloudify all of these distributions. So AWS has a thing called EMR that I think was based on Cloudera. I think Azure has HD Insight, which I think was based originally on Hortonworks. And of course, these have matured and developed over time. Cloudera themselves had a hybrid multi-cloud offering. But basically, this kind of became the go-to architecture for massive horizontal scaling. You could just go to AWS and say, give me the biggest EMR cluster you have, and you'd have a Spark environment that you could do lots and lots of processing. So this is kind of what they base their SageMaker and some of those other pieces on in terms of the processing, things like Glue and some of the other AWS things that they have. So again, the basic idea here is there's not one name for this. You can't really call it Hadoop because Hadoop doesn't necessarily belong in there anymore. You could call it Spark because that's kind of the centralized piece of it, but there are many, many other pieces that go along with it. So that's probably not sufficient. The advantages of this particular set of solutions is, well, for one thing, it scales horizontally very, very well, which doesn't necessarily provide you speed, but it provides you capacity. So you can generally get pretty good performance on a steady basis as you add more and more data, and you can scale out very easily. There are a ton of options in terms of how you can architect your solution. Like I said, one of the more creative ones was having a relational database built on top of a Kafka stream. But there are tons and tons of options about what you can do in terms of languages that you can use, in terms of architectures that you want to implement. There's pretty well established, for example, IoT models based on this architecture that are pretty much out of the box, ready to go. Again, it allows whatever to scale without code changes. So if you start out writing what you're doing in PySpark, which is just Python, pretty easy to do. As you add more and more data and you scale out your system, you're not making code changes. It just works the way that it is. With this system, you do get schema inference at acquisition. So as data comes in, you know what it is. You can tell that it's different from some other piece of data. It gives you a leg up on being able to do that auto detection of what you're dealing with piece. There's a much reduced data loading overhead. So if you think about the idea of using a relational database and having to load data into a relational database and all the gotchas that go along with that, this is as easy as copying a file into a directory in most cases, and that fast. Now, it doesn't mean you don't have to deal with downstream concerns, but in terms of actually getting the data to the place where you can start looking at it, it's very fast. And that helps to facilitate that repeatable whatever piece, because it's realistic to say, hey, I'm gonna load my data 5 times today, and I'm gonna load a bunch of different data 5 times today, and it's realistic to think that could actually take place in that time frame. And then, of course, there are many, many options for what's available at consumption. Using SerDes and things like the Hive catalog. There are lots of ODBC, JDBC drivers, OData drivers, and this platform can really export to any kind of format very, very easily, CSV, JSON, you know, probably YAML, but certainly XML, and then lots and lots of binary formats that would be useful. So just to end this up, the reason that I mentioned this piece last is that this is a lot of what I talked about has sounded a little bit abstract and theoretical, but it's really not. It's actually quite mature at this point. Some of these things are going on 10 to 12 years of very heavy usage, and even longer than that. So that's the end of what I wanted to talk about. I do want to acknowledge the PIs on the NAN project, because I wouldn't be speaking here with you without their support in what I'm doing. So thank you to them. And thank you all for listening. If there are any questions or anything I can answer, please let me know.